In many applications of linear algebra, it is important to talk about subsets of a vector space that are themselves vector spaces too. These are called vector subspaces, and they are the subject of this lecture. So let me write down the definition. A non-empty subset, W, of some vector space V is a subspace if it is both closed under addition and scalar multiplication. So notice here that being closed under addition and closed under scalar multiplication, those are axioms number 1 and 6 on our list of the axioms that make up a vector space. And the notion here is that if W is a subset of V, then all of the other axioms are going to be automatically inherited from the parent vector space V. A canonical example of this are R1 and R2 sitting inside of R3. R1 is a subspace of R2 and R2 is a subspace of R3. This is easy to visualize by thinking of a line or a plane inside of three-dimensional space, but also we can work this out with vectors as well. See, if you take a vector in R1, that's going to be a number. And if you take a linear combination of two of them, when they're sitting inside of R3, you would be looking at vectors of this form, x1, 0, 0, x2, 0, 0. So this is something in R1. And if you add it to something else in R1, you produce something else that stays in R1. And you can see this because the second and third coordinates are going to remain 0, no matter whether you scalar multiply or add them together. Likewise, if you take something that lies in R2 in a plane and add it together, it's going to stay in R2. We can make a very quick test to see whether something is a subspace. It's easier to check whether something is a subspace of a vector space than whether to check that an arbitrary set is itself a vector space. So if you have a non-empty, and it must be non-empty so that the zero vector lives in it, non-empty subset of V, all you need to check is that it's closed under vector addition and closed under scalar multiplication. If both of these are true, then you have a subspace. You do not need to check the distribution property, associativity, commutativity of addition. All of those other axioms are going to be inherited from V. You only need to check that it's closed under addition and scalar multiplication. So now let's look at some examples. So why don't we look at a vector subspace of the vector space that's comprised of 2 by 2 matrices. So we know from our previous discussion that the space of 2 by 2 matrices is a vector space. You can add 2 by 2 matrices together and get another 2 by 2 matrix. You can do scalar multiplication, and all of the other axioms are going to be satisfied. Now we're going to take a subset of M22. This is matrices that are 2 by 2. And we want to restrict to the symmetric matrices, so only things that are symmetric. The first thing to notice is that W is non-empty. It's easy to find examples. You could take the zero vector in this vector space, meaning the 0 2 by 2 matrix, or your favorite symmetric 2 by 2 matrix, and these are in W. Let's give ourselves a little bit more space to work with on this page, and then continue with this example. So we're going to be using our test for a subspace. We want to see that in this example, it's closed under addition and closed under scalar multiplication. To see that it is indeed closed under vector addition, let's take matrices A1 and A2 in W. So these are some arbitrary symmetric matrices. Remember that a symmetric matrix is one that's equal to its own transpose. So there's a quick rule we can use here. A1 plus A2 transpose is the same thing as A1 transpose plus A2 transpose, and that's equal to A1 plus A2, since each of A1 and A2 is on its own symmetric. And so that allows us to see that A1 plus A2 itself is symmetric, and so it's in W. This notational trick of using the transpose is really just a concise way of saying that when you add two symmetric things together, you're going to get two symmetric things. You could also do this with a component-wise kind of argument. Next, you check that it's closed under scalar multiplication. And that's also going to be true. If you take a scalar multiple of A, and then you transpose it, this is equal to the scalar times A transpose, and A is equal to its own transpose because it is symmetric. And so since CA is equal to its own transpose, it too is a symmetric matrix, meaning that we have something that is closed under scalar multiplication. So by the test for a subspace, we see that W is indeed a subspace of the vector space of 2 by 2 matrices. In the next example, we're going to see something which is not a subspace. So for this example, let's take not the set of symmetric matrices, but instead the set of singular matrices. So still we're looking at subsets of M2 too, but now we're going to be looking at matrices whose determinant is 0. Matrices whose inverse does not exist. That's what it means to be a singular matrix. So the issue here is that we're going to be able to rig up an example, let's make some space for it, of matrices which are singular, but when we add them together, we get something which is not singular. And that means it's not going to be closed under addition. So our counterexample is going to be made out of something like, let's take A1 to be 1, 0, 0, 1, 1, 0, 0, 0, and A2 to be 0, 0, 0, 1. All right, so each one of these is on its own singular and cannot be inverted. The determinant of A1 is 0, and that's equal to the determinant of A2, also 0. But when you add them together, you get the identity matrix, which has determinant 1 and is non-singular. The problem here is that we can add two matrices from this set together when we go outside of the set. So it's not closed under vector addition. And so singular matrices do not make a subspace of the 2 by 2 matrices. One useful statement is that the intersection of two subspaces is a subspace. In other words, if U and V are subspaces of some vector space W, then U intersect V is also a subspace of W. Let's prove this. So as a reminder, what we need to show is contained in this test for a subspace. And even though there's an itemized list with 2 items on it, there's really 3 things to check. So the statement here is that if W is not empty, it's a non-empty subset of V, then you have to check 2 things. So really that means the first thing is we need to check that the intersection, U intersect V, in our problem up here, we need to see that U intersect V is not empty. And then after we've established that it's not empty, we need to see that it's closed under addition and it's closed under scalar multiplication. So these are the 3 things that we'll establish in our proof. And I'll leave this test over here as a reminder. Okay, first it's easy to see that the intersection of these 2 subspaces, U and V, is not empty. You simply have to note that because U and V are on their own subspaces of W, they both contain the 0 vector. So the 0 vector is in U, and the 0 vector is in V, and so that means that the 0 vector is in U intersect V, because it belongs to both of those sets. Next, we're going to check 1 and 2, the closure under addition and scalar multiplication, simultaneously. So for this, what we would like to do is take something that is in U intersect V, take 2 things in there, and make sure we can add them together and scalar multiply them and remain in the same place. So we are going to let vectors, say V1 and V2, belong to U intersect V. If V1 and V2 are in U intersect V, then they're also in U and they're also in V. So what we can say is then a linear combination CV1, so scalar multiplication, and the addition with D, V2, this linear combination belongs to U because U is closed under these operations. And this same linear combination belongs to V because V is closed under these operations. And so that simply means that CV1 plus DV2 is also in U intersect V. Therefore, U intersect V is a subspace by the subspace check, and that's all there is to it.